Alright, so we are going to do some energy and light equations. Now, first, we got to look at our frequency, or our equation. If a wave has a wavelength of 480 nanometers, calculate the frequency. So our equation is C equals F times wavelength. Okay, F is frequency, and this thing here, this is called lambda, that means wavelength. Okay, and then C is a constant. It stands for the speed of light, which the speed of light is always going to be either 3.00 times 10 to the 8th meters per second, or 3.00 times 10 to the 17th nanometers per second. Now, the way that we determine which one of those we use is we look at our problem and we see what we have in our problem. This has 480 nanometers, so since we have 480 nanometers in our problem, we're going to use this one, which has nanometers there. Okay. Next, we need to find the frequency. That's our unknown. So we got to get frequency by itself. So the way we do that is we divide both sides by wavelength. Wavelength over here cancels out. So now we are left with C over wavelength equals frequency. Okay, so now we just plug everything in. C, which we said is going to be 3.00 times 10 to the 17th nanometers per second, divided by the wavelength, which is 480 nanometers, and we get 3.00 times 10 to the 17th divided by 480. We get 6.25 times 10 to the 14th. Okay, and then nanometers cancels out. We're left with 1 over seconds, which is the same as saying hertz. Okay, so that is our answer for that. Next, if there is a wave with a frequency of 4.56 times 10 to the 14th hertz, calculate the wavelength in nanometers. So again, we're using the same equation, C equals F times lambda, but this time we're looking for wavelength. So we got to get wavelength by itself. So same idea, we're just going to divide both sides by F instead of lambda. F is going to cancel out, and we're going to be left with C over F equals lambda. So again, same idea. We take our speed of light, which again we're going to use 3.0 times 10 to the 17th because we want our wavelength in nanometers, so we're going to use nanometers. So 3.00 times, whoops, that's weird, times 10 to the 17th nanometers per second, divided by our frequency, which is 4.56 times 10 to the 14th hertz. We enter that in our calculator. 17 divided by 4.56 times 10 to the 14th. And we get 657.89. Hertz, like I said, is the same as per second, so hertz cancels out with per second, and we're left with nanometers. And then there's our answer. All right, last one. If a wave has a frequency of 567 times 10 to the 9th hertz, calculate its energy. Now, this is a different equation. This is our energy equation, which is E equals H times F. Now, H is a constant. It's called Planck's constant. And H equals 3.989 times 10 to the negative 13th. And that's kilojoules. Seconds per mole. I ran out of room, but but you get the idea. Kilojoules seconds per mole. Okay, so all we gotta do here, we don't have to rearrange the equation at all because we're looking for energy, and energy is already by itself. So we just take H times our frequency, so 3.989 times 10 to the negative 13th kilojoules seconds per mole multiplied by our frequency, which is right here, 5.67 times 10 to the 9th hertz. And then, sorry, I ran out of room here. Let's erase that. Okay. All right, equals, and then we put that in our calculator. Probably should have done that while I was erasing, but sorry, gotta wait a second. Times 5.67 times 10 to the 9th, and that equals 0.00226. And so our units are going to be, seconds cancels out with hertz, so our units are going to be kilojoules per mole. And that is that.